Today we'll discuss ISI's B-Math 2011 subjective paper, and the first question is, let a greater than equal to 0 be a constant such that sine under root x plus a is equal to sine under root x for all x greater than equal to 0. Then what can you say about a? Justify your answer. This is sine theta equals sine alpha. We'll write its general solution. So its general solution will be theta, which in this case is under root of x plus a equals n pi plus minus 1 to the power n alpha, which is under root x. Now we'll square both sides. We can write x plus a equals n square pi square plus x plus minus 1 to the power n 2n pi into under root x. Now here x and x will cancel. We can write this a as n square pi square plus minus 1 to the power n 2n pi into under root x. Now this is true for all x greater than equal to 0. That means this a, it should be independent of x, and it will be independent of x if and only if n is 0. Now if we put n as 0, we'll get the value of a as 0. So this condition is satisfied if and only if a equals 0. Now question number 2 is, let fx equals e to the power minus x for x greater than equal to 0. Define a function g on the non-negative real numbers as follows. For each integer k greater than equal to 0, the graph of the function g on the interval k to k plus 1 is a straight line segment connecting the points k fk and k plus 1 fk plus 1. Find the total area of the region which lies between the curves of f and g. Now we'll draw the two curves. This is our axis, and then we'll draw the graph of e to the power minus x. So that's the graph of y equals e to the power minus x. Now for some point k and another point k plus 1, we have 2 points on the curve which are k comma fk and k plus 1 comma f k plus 1, and if we join these 2 points we get a straight line, and this function is your gx. Now we need to find area between these two curves, and suppose this area is AK. Now AK is given by area of this trapezium, and area of this trapezium will be 1 by 2, and then what is Fk? Fk is e to the power minus k, so it will be e to the power minus k plus e to the power minus k plus 1 into h, and h in this case is 1 minus area bounded by this curve e to the power minus x. So it will be integral from k to k plus 1 e to the power minus x dx. Now we can write this ak as 1 by 2 e to the power minus k plus e to the power minus k plus 1, and here will be e to the power minus x from k to k plus 1. So this ak will be 1 by 2 e to the power minus k plus e to the power minus k plus 1 plus e to the power minus k plus 1 minus e to the power minus k. Now we can write this as 3 by 2 e to the power minus k plus 1 minus 1 by 2 e to the power minus k. Now we'll take 1 by 2 e to the power minus k common. We can write this as 1 by 2 e to the power minus k 3 upon e minus 1, which is e to the power minus k 3 minus e upon 2e. Now we need to find total area of this region. Now total area of this region, it is given by this summation k varies from 0 to infinite ak. Now we take this summation, we can write this as 3 minus e upon 2e, and then this summation e to the power minus k, where k varies from 0 to infinite. Now this is nothing but a gp, so we can write this as 3 minus e upon 2e, and this is a upon 1 minus r, and r in this case is 1 upon e. So e and e will cancel. So this area will be 3 minus e upon 2 into e minus 1. So this total area of this region, which lies between curves f and g, is 3 minus e upon 2e minus 1. Now question number 3 is, for any positive integer n, show that 1 by 2 into 3 by 4 into 5 by 6 up to 2n minus 1 upon 2n, it is less than 1 upon under root of 2n plus 1. Now let this statement be Pn. Now we'll solve this question using mathematical induction. Now we'll prove this result for n equals 1. Now for n equals 1, on the left hand side we have 1 by 2, and on the right hand side we have 1 by under root 3, which is true. That means P1 is true. Now second step is, we'll let Pk be true. That means 1 by 2 into 3 by 4 up to 2k minus 1 upon 2k, it will be less than 1 upon under root of 2k plus 1. Now we have to prove this result for pk plus 1. Now for pk plus 1, we can write this as 1 by 2, 3 by 4, 2k minus 1 upon 2k into 2k plus 1 upon 2k plus 2, and we know that this result, it is less than 1 upon under root 2k plus 1. So we can write this as 1 upon under root of 2k plus 1 into 2k plus 1 upon 2k plus 2, which is under root of 2k plus 1 upon 2k plus 2. Now if pk plus 1 is true, we need to prove that this expression, it is less than 1 upon under root of 2k plus 3. So what we'll do is, we'll start from here and we'll see if this result is true. So what we'll do is, we'll square it and we'll cross multiply. We can write 4k square plus 8k plus 3, it is less than 4k square plus 4 plus 8k, which is true for all k. That means this statement pk plus 1 is true. So from mathematical induction, we can say that this result is true for all positive integer n. Now question number 4 is, if a1, a2 up to a7 are not necessarily distinct real numbers such that ai lies between 1 and 13 for all I, then show that we can choose 3 of them such that they are the lengths of the side of a triangle. Now without loss of generality, we can say that a1 is less than equal to a2, is less than equal to a3, and is less than or equal to a7. We'll prove this result using contradiction. So what we'll assume is, we'll say that we can choose three numbers such that they do not form a triangle. Now a7, a6 and a5, they do not form a triangle, which simply means that sum of two sides must be less than or equal to this third side. So we can write a7, it must be greater than or equal to a6 plus a5. And the same way we can write a6 must be greater than a5 plus a4. So we can write 2a5 plus a4. Now again a5 is greater than or equal to a4 plus a3. So it will be greater than or equal to 3a4 plus 2a3, and a4 is greater than or equal to a3 plus a2. So it will be greater than or equal to 5a3 plus 3a2. Now again a3 is greater than or equal to a2 plus a1. So it will be greater than or equal to 8a2 plus 5a1. Now each of ai, it lies between 1 and 13. So a2 will be greater than 1 and a1 is also greater than 1. So from here we can say this a7 will be greater than 8 plus 5, which is 13. But it is given that ai, it lies between 1 and 13. So we have a contradiction here. So from contradiction we can say that we can always find three numbers such that they are the lengths of the sides of a triangle. Now question number 5 is, let n1 equals 2, n2 equals 3 and 3 equals 5 be the sequence of non-square positive integers if the nth non-square positive integer satisfies m square less than nn less than m plus 1 whole square, then show that m equals greatest integer function of under root n plus 1 by 2. Now if we consider square numbers, there are 1 square and then 2 square, 3 square. Now between 1 square and 2 square we have 2, 3. Here we have 5, 6, 7, 8. Now 10, 11, 12, 13, 14, 15, and then we have 4 square, and then we'll have m square followed by m plus 1 square. Now between 1 square and 2 square we'll have 2 non-square numbers. Between 2 square and 3 square we'll have 4 non-square numbers. Between 3 square and 4 square we'll have 6 non-square numbers. Between m minus 1 square and m square we'll have 2 m minus 1 numbers, and between m square and m plus 1 square we'll have 2 m numbers. Now this nth number, it will lie somewhere here. Now if the nth number lies between m square and m plus 1 square, then this n, it will be greater than sum of all these numbers, which is 2 plus 4 plus 6 up to 2m minus 1. So it will be 2, 1 plus 2 plus 3 up to m minus 1, and it will be less than or equal to all the numbers till m plus 1 square. So it will be 2 into 1 plus 2 plus 3 up to m. Now we can write this as 2 into m minus 1 into m by 2 will be less than n, will be less than equal to 2 m plus 1 by 2. Here 2 and 2 will cancel. So we can write m square minus m, it is less than n, it is less than or equal to m square plus m. Now m square minus m and m square plus m, they are all integers. So we can write m square minus m, it will be less than n minus 1 by 4, will be less than m square plus m. Now if we add 1 by 4, we can write m square minus m plus 1 by 4, it is less than n, it is less than m square plus m plus 1 by 4, which is m minus 1 by 2 whole square is less than n, and it is less than m plus 1 by 2 square. Now from here we can write m minus half, it is less than under root n, it is less than m plus 1 by 2, or m is less than under root n plus 1 by 2, and it is less than m plus 1. So from here we can say this m, it must be greatest integer function of under root n plus 1 by 2. Now question number 6 is, let R and S be two cubes with sides of lengths R and S respectively, where R and S are positive integers. Show that the difference of their volumes equals the difference of their surface areas if and only if R equals S. Now what we are given is, we are given that difference of their volumes, which is R cube minus S cube, it is equal to difference of their surface areas, which is 6 times R square minus S square. Now we can cancel R minus S. That means one result that we'll get here is R must be equal to S, and then we'll be left with r square plus s square plus r into s will be equal to 6 r plus s. Now here if we take r common, we can write r into r plus s square equals 6 into r plus s, or s square is r plus s into 6 minus r. Now s square is greater than 0. That means from here we can say the value of r must be less than 6. Now in the same way, we write the expression for r square, we'll get this other condition, which is s is also less than 6. Now what we'll do is we'll come back to this and we'll take everything on the left hand side. We can write r square plus s square minus 6r minus 6s plus r into s equals 0, and we'll multiply it with 2. So this is 2, this is 2. Here it will be 12 and 2rs. Now we can write this as r square minus 12r plus s square minus 12s plus r square plus s square plus 2rs, and this is equal to 0. Now we'll complete this perfect square. We'll add 36 in both the expressions, and here on the right hand side it will be 72. So we can write this as r minus 6 square plus s minus 6 square plus r plus s square, and it is equal to 72. Now right hand side, it is divisible by 4. So this left hand side, it must also be divisible by 4. Now we know that any square, it is congruent 0 or 1 modulo 4. Now from here we can say both these r and s, they are even numbers. So now we have this condition that r and s, they are even, and r and s, they are less than 6. They can take the value either 2 or 4. Now if we choose r as 2, then here will be 2 minus 6, which is 4. 4 square is 16. And if we choose r as 4, here will be 4 minus 6 minus 2 square is 4. So it will be either 16 or 4. And the same way for s minus 6, it will also be either 16 or 4. And what about r plus s? R plus s will be either 4 or 6 or 8. Now 4 square is 16, 6 square is 36, and 8 square is 64. Now this expression is 72 if either it is 16 and 36 or 4 and 64. But if we choose 16 or 4, again we'll end up getting this condition that r equals s. So this equation is true if and only if r equals s. Now question number 7 is, let ABC be any triangle and let O be a point on the line segment BC. Show that there exists a line parallel to AO which divides the triangle ABC into two equal parts of equal area. Now we are also given this figure. Now what we can do is we can write area of triangle OAB upon area of triangle ABC will be equal to OB upon BC, and let us say this is R. If R equals 1 by 2, then it's a trivial result. We need not prove anything. So without loss of generality, we'll assume that this R is greater than 1 by 2. Now we'll take a point A dash on AB and O dash on OB such that AO dash is parallel to AO. So A dash O dash is parallel to AO, and we'll choose these points A dash and O dash in such a way that BA dash upon AB equals BO dash upon BO equals A dash O dash upon AO, and let it be equal to 1 upon under root 2R. Now we write area of triangle A dash O dash B upon area of triangle AOB. This ratio is equal to A dash O dash upon AO square, and which is 1 upon 2R. Now we'll take area of AOB on the right hand side. We can write area of A dash O dash B, it is 1 by 2R into area of AOB, and area of AOB is R times area of ABC. So we can write 1 upon 2R into R times area of ABC. Now this R and R will cancel. So from here we can say area of triangle A dash O dash B is half the area of triangle ABC. So this is how we have proved that there exists a line parallel to AO which divides the triangle into two equal parts of equal area. Now question number 8 is, we are given that T1 is less than T2, is less than T3, it is less than T99, be real numbers, and consider the function f from R to R given by fx equals this summation I varies from 1 to 99 mod of x minus ti. Now if we find f dash x, then this f dash x will be this summation I varies from 1 to 99 and then signum of x minus ti. Now we know that any signum function is either plus 1 or minus 1 or it is 0. Now in this expression we have 99 terms. So this f dash x will be 0 if we have 49 plus 1s, 49 minus 1s and 1 0. And this is possible if we choose this x to be T50. So f dash T50, it will be 0. So we have a critical point at T50. Now we need to show that at this point it will be a minimum. Now if we find f dash T50 negative, then each of the signum function from 1 to 49 x minus ti, it will be a positive number. So the signum function will be plus 1 plus 1 plus 1 49 times. So it will be simply plus 49. Now from 50 to 99, this expression will be negative. Now from 50 to 99, it will be minus 1 each. So it will be minus 50. So this derivative is minus 1. So f dash T50 negative, it is less than 0. And we can write f dash T50 positive, it will be plus 50 and minus 49, which is plus 1, which is greater than 0. That means at 50, sign of derivative, it changes from negative to positive. And if the sign of derivative changes from negative to positive, that means this T50 is a point of local minimum. So minimum value of this function will occur at T50.